In the last lesson, and in fact the last couple lessons, I said that a system of two equations with two unknowns usually has a single unique solution. Altogether, there are three cases. There's the case of one unique solution for x and y. There's the case of an infinite number of solutions. Then there's the case of no solution possible, no solution at all. Now, in the previous lessons, we discussed case one already. We discussed that in great detail, how to find the solution, the single solution, either by substitution or elimination. I will remind you, that case corresponds to a case in which two lines in the xy plane intersect at a single point. So usually, you pick one random line, another random line, and what happens is you're just going to get those lines intersecting at a single point. So that is by far the most common case, but it's not the only case, and there are two other cases possible. Case two is the infinitely many solution. So I'll say pause the video and try to solve this system on your own. Okay, let's talk about this. The first equation has a negative y, so this is an easy candidate for substitution. We get y equals 2x minus 5. Very good. Plug this right into the second equation. Very good. Then distribute, then cancel. And wait a second. All the x's went away. What exactly is going on here? So if you get to a point where all the x's suddenly disappear, suddenly there are no variables and they're just numbers, don't automatically assume that you've done something wrong. On this page, every single step I followed was mathematically correct, and it wound me up here at negative 10 equals negative 10. So what exactly is going on here? We started with the system and ended up with an equation, negative 10 equals negative 10. In other words, an equation that is always true. It doesn't matter what x or y equal. It's always going to be true that negative 10 equals negative 10. That is true 100% of the time. So it is a truth not dependent on the values of x and y. Well, that means if we wind up with something that's always true, we must have started with something that was always true. It means that the starting point, the system, must be always true. That is true for all values of x and y. No matter what we make the values of x and y, we will have a system that works. We will have a true system. How did this happen? Let's go back and look at the original equations. Rewrite the second equation. We'll just put the x first. Now multiply the first equation by negative 2, and lo and behold, it's the same equation. One equation is just a multiple of the other, so it's really just two copies of the same equation. At the beginning of the video on two equations and two unknowns, we discussed how a single equation with two variables would have an infinite number of solutions. That's exactly what we have in this system, because really we have, it looks like two equations are written on the page, but really it is just two copies of the exact same equation. We really have only one equation. And one equation, as we know, two variables, one equation, we have an infinite number of solutions. In a way, we're asking, where does a line intersect itself? It's as if we pick two random lines, and by the most unlucky chance imaginable, we just happen to pick the same line twice. And so it lands on itself and intersects itself in an infinite number of places. If you notice that one equation is a multiple of the other, that means you are in the infinitely many case. Sometimes you can just spot that. Even if you don't notice that and solve, you'll wind up with an always true equation. You wind up something where all the variables drop out, and you just get something like 7 equals 7, something that's always true. When you get something that's always true, that's an indication that the system of equations is also always true for all values of x and y. So this is the infinitely many solutions case. Now let's talk about the no solutions case. Pause the video and try to solve this system. Okay, much in the same as the last time. We have an x by itself, so that's a very obvious candidate for substitution. X equals 2y plus 5. Very good. Now plug that into the second equation, distribute, cancel, and what's going on here? Again, all the variables have dropped out, but now we have something that is patently false. It is never true that 15 equals 8. We've run into a contradiction. Here we started with the system of equations and it led us to a never true equation. This means that the system of equations must be never true. In other words, there's no possible values of x and y that we could pick that would allow us to say that 15 equals 8 is a true statement. So the system does not work for any values of x and there is no solution. How can this happen? Think of the original system again. Multiply the first equation by 3, and what we get is 3x minus 6y equals 15. And notice we have the same expression on the left in both equations equal to different things. We have the same expression equal to two different things. That's impossible. There's no way that 3x minus 6y can equal both 8 and 15 at the same time. And that's why we were led to the paradox 8 equals 15. In terms of the graph, this would be the case of parallel lines. We pick two lines at random, and just by pure chance, we happen to pick two parallel lines. In a way, we're asking, where do the parallel lines intersect? The answer, of course, is that they don't. Parallel lines never intersect. If you try to solve the equation and your work results in a never true equation, you wind up with something like 2 equals 7, then it means that the system is never true. It has no possible solutions. In summary, a system of two equations with two unknowns may have one solution, no solutions, or infinitely many solutions. The most common case by far is the one solution case, and that's where you would use substitution or elimination and solve for individual values of x and y. If you do that solving and you get an always true equation, something like 12 equals 12, then the system is always true. It has infinitely many solutions. If you solve and all the variables drop out and you wind up with a never true equation, something like negative 2 equals positive 9, then the system has no solutions. Now we'll talk about the three equations with three unknown case. The very first thing I'll say is that this is an awfully rare scenario. It's unlikely, unless you're doing very well, that you're going to be handed something like this. But it could show up, so it's worthwhile talking about this. So, suppose we have this particular system. We have three equations and three unknowns. Now, of course, I haven't given a question here, but let's just assume that for whatever reason, we need to solve for the individual values of all three variables. Well, a few thoughts first of all. Big idea number one. If the number of equations is fewer than the number of variables, you will not be able to solve for the individual values of the variables. If you have two variables and only one equation, you can't solve for those individual values. If you have three variables and two equations, you can't solve. In order to solve for individual values, you need to have three equations with those three variables. Big idea number two is quite subtle. Depending on what the question asks, you may not have to solve all the way. Now this is tricky. Sometimes the question will say, what's the value of x? What's the value of y? They'll want to know a specific variable. Sometimes, though, they'll ask about an expression. What's the value of x plus y? What's the value of x minus z? What's the value of x plus y plus z? Something like that. Often when the test does that, there's a much shorter way to solve directly for the value of the expression without solving for the individual values of the variables. So always keep your antenna up for these kinds of shortcuts. If you can go directly to the answer without doing all the work of solving all the equations all the way, by all means do so. Finally, big idea number three, inside every big problem is a little problem struggling to get out. Now, of course, this is kind of a playful way to say it, but it turns out in mathematics, much of mathematic problem solving consists of reducing problems you don't know how to do to problems you do know how to do. Now, this is true not only at the level of the test, but even at the level, say, of calculus and beyond calculus analysis, topology, even all the way up to PhD levels in mathematics. The way that new math gets done at the PhD level is that mathematicians are reducing problems that we, the human race, doesn't know how to do, reducing them to problems we do know how to do. So it turns out this is a very sophisticated strategy, and it's It's a very important perspective in your problem-solving abilities on the test. Now, in this particular case, I'll show you what I mean. So here we have three equations with three unknowns, and I've labeled the equations. Well, theoretically, you've watched these videos, and so you know how to solve two equations with two unknowns. That we've covered already. So now we want to know how to do this. So what we're going to do is take a series of steps that will allow us to change three variables with three unknowns into two variables with two unknowns, because that's something we know how to do. Well, first thing that catches my eye, notice we have a plus x and a minus x. That really just kind of jumps out at me. It's kind of a screaming sign as far as I'm concerned in these equations. What that means is I could add those two equations and eliminate an x. So I'm going to add b and c. b is 2w plus x minus 4y equals negative 14. c is 3w minus x plus 2y equals 8. Add them up, add everything straight down, we get 5w minus 2y equals negative 6. I'm going to call this equation D. This is now one equation that has two unknowns. So by itself it's not very useful, but if we could get another equation with the same two unknowns, then we'd be in business. So we want to pick another pair of the three original equations, a different pair, so not B and C this time, a different pair, and see if we can eliminate x again in this new pair, because if we eliminate x again, we'll get another equation that has just w and y in it. So again, this plus x looks like it would be pretty easy to cancel it with this minus 2x. If I just multiply b by 2, then that should be able to cancel them. So I'm just going to have a by itself. A is w minus 2x plus 3y equals 13. I'm going to multiply 2 times b. So everything on both sides of the equation gets multiplied by 2. Of course, you're always allowed to multiply both sides of an equation by the same thing. That's perfectly legitimate. That will give me 4w plus 2x minus 8y equals negative 28. All right, so very good. So now, again, add straight down. I get 5w, the x's cancel as predicted. I get negative 5y equals negative 15. Now, ordinarily, I would say, gee, all of these are multiples of 5. Wouldn't it be easier to divide by 5, get smaller numbers? Then that might make it very easy to cancel, to substitute, to do all kinds of things. But I'm not going to do that only because, I'm going to call this equation E as is, only because I notice I have a 5w here and a 5w here. Wow, those are kind of screaming out to me now. Can I just solve for 5w for both of these equations? 5w equals 2y minus 6. 5w equals 5y minus 15. So if these two things both equal 5w, they must be equal to each other. So this is an example of substitution. We're going to set these equal. 5y minus 15 equals 2y minus 6. Well, now I'm down to one equation with one unknown. This is great. I know how to solve this. So subtract 2y from both sides. We get 3y minus 15 equals negative 6. Add 15 to both sides, 3y equals 9. Divide by 3, we get y equals 3. Okay, and of course we know with the two equation, two unknown case, once we get the value of one variable, we just plug it in. We could plug it into this one or this one, doesn't matter. This one looks like it has smaller values, so I'll just plug it in there. 5w equals 2y, which is 6, minus 6, equals 0. That's funny. If 5y equals 0, 5w equals 0, that means that w must equal 0. Okay, very interesting. That can happen sometime. W equals 0. So now I have the value of w, the value of y. I'm almost done, but I need the value of x. So now I actually have to go back to one of the original equations. Let's take the top one, a. W, that's 0, minus 2x plus 3y, so 3 times 3 is 9, equals 13. Subtract 9 from both sides, I get negative 2x equals 4, or x equals negative 2. And those are the three values of the three variables from these equations. Again, notice that the strategy I used was to reduce the 3 equation 3 unknown scenario to a 2 equation 2 unknown scenario. So just to summarize, first of all, I'm going to pick 2 of the 3 equations, and using either substitution or elimination, eliminate 1 variable. Incidentally, 99% of the time, it's going to be much easier to use elimination rather than substitution. Then I'm going to pick another pair of those original equations and similarly eliminate the same variable. So at this point, I will be down to the 2 variable with two equation case. Now, just use the 2 equations with 2 unknown techniques. We've learned those already. Solve for those 2 variables. When you have the numerical values of those 2 variables, finally, plug into any of the original equations to find the value of the 3rd variable. This is exactly how you solve this scenario. Now we'll begin a section on advanced algebra, kind of a grab bag of advanced topics in algebra. First thing we'll talk about are absolute value equations. Recall what we said about absolute value in the lesson Positive and Negative Numbers 2 in the Arithmetic and Fraction modules. If you haven't seen that module yet, and you haven't seen that lesson, I'd suggest looking at that first and getting a good sense about absolute value before we go through all the information in this lesson. So, we'll begin with a simple observation that, for example, absolute value of positive 5, of course, is positive 5. Absolute value of negative 5 is, of course, positive 5. So either of these equations, absolute value of 5 equals x, or absolute value of negative 5 equals x, would have the single solution x equals 5. Those are not very interesting equations. Not very interesting when there are no variables inside the absolute value. It gets more interesting when we put variables inside the absolute value. So the absolute value of x equals 5. Think about that. That has 2 solutions, positive 5 or negative 5. X could be either one of those values. And this is similar to the way that a quadratic equation has 2 solutions. So this is another category of algebra equations that can have 2 solutions. Suppose an expression other than x is inside the absolute value. So for example, the absolute value of the quantity 2x plus 3, and all that's going to equal 5. Well, of course, if that whole expression has an absolute value of 5, then there's only 2 possibilities for it. Either the expression inside equals 5 or it equals negative 5. So it's very much the same approach. We're going to set that expression equal to 5 and set it equal to negative 5. And of course, this is connected by the word or. And remember, exactly the same way with quadratics, this word or is a mathematical object. It's not a piece of garnish. It's a necessary part of the problem. So we solve the equations individually, and we get x equals 1 or x equals negative 4. And those are the 2 possibilities. Generalizing, we could say that if E is any algebraic expression and K is any positive number, then the equation absolute value of E equals K has the solutions E equals positive K or E equals negative K. I should hasten to add here, this notation I'm using E for an expression, I just made this up on this page. This is not a general notation that you're going to see anywhere else. I'm just using it for shorthand here. The idea is that we could put any expression inside the absolute values, and then whatever it equals, whatever that absolute value equals, the expression itself would equal the positive or negative of that same value. Notice, if the absolute value is not by itself on one side, we will have to isolate it before we can break it into the 2 or equations. Here's a practice problem. Pause the video and then we'll talk about this. So of course with this, we have to isolate the absolute value first. We subtract 1. Once we subtract 1, then we're all set. I'm going to break it into two equations. Solve each equation individually, divide by 3, and we get x equals positive 2/3 or x equals negative 2. And those are the two solutions. What if the absolute value of an expression equals not a single number, but an other expression? So now we're actually getting into the territory that the test would actually ask us. We'll still follow the same plan. So absolute value of anything equals something else. It means that that thing inside the absolute value, a, equals either positive b or negative b. So it equals either the expression on the other side or the expression on the other side with a negative sign in front of it. Sometimes this will give us extraneous solutions, solutions that result correctly from the math, but which don't work in the original equation. We have to check each solution. So this is an odd thing about absolute value equations, and we'll see this again much later on when we talk about square roots also, that we get extraneous solutions. So that means we have to check our work, check the answers that we find. So here's a practice question. Pause the video, work on this, and then we'll talk about this. Okay, for this one, the absolute value is already isolated, so we can immediately break this into the OR equation. So we say that the thing inside the absolute value, 1 plus 2x, either equals that expression, 4 minus x, or equals the expression with a negative sign in front of it. And of course, putting a negative sign in front of subtraction just reverses the order of the subtraction. It becomes x minus 4. So the first thing we're going to do is we're going to get all the x's on one side in each equation, then subtract the 1 and isolate the x, and then divide, and we get the solutions x equals 1 and x equals negative 5. Now we're not done here. We did the correct math, so these two solutions correctly result from the math, but we don't know, do they actually satisfy the original equation? So we have to check. So for x equals 1, I plug it into the left side, I get 3. I plug it into the right side, I get 3. So that works. For negative 5, I plug it into the left side, I get 9. I plug it into the right side, I get 9. So that also works. So both answers work here. So here we have two valid solutions to the equation. Here's a practice question. Pause the video, work on this, and then we'll talk about this. Okay, again, the absolute value is isolated, so we can go directly to the OR equation. So the thing inside, x plus 4, that's either going to equal the expression or equal the expression multiplied by a negative sign. So the first thing we're going to do is get all the x's on one side. Then we're going to subtract to isolate the x, and we get either x equals 1 or x equals negative 1.5 or negative 3/2. So now we'll plug these in and check these. Those are our two solutions. For positive 1, when we plug that into the left side, we get 5. When we plug it into the right side, we get 5. That checks. That's perfectly fine. Negative 1.5, when we plug this into the left side, we get 2.5. When we plug it in to the right side, we get negative 2.5. So this doesn't work. It gives a different value on the right and left side when we plug in. So this doesn't work, and this equation has only one solution, x equals 1. Here's another practice question. Pause the video and then we'll talk about this. So we can go directly to the OR equation. The thing inside, 2x plus 5, either equals x plus 1 or equals x plus 1 multiplied by a negative sign. We'll group the x's on one side. We'll subtract the 5. Then we have to divide by 3 in the second equation. So we get x equals -4 or x equals -2. So these are our roots. So we have to check these roots now. Check the first one, x equals -4. When we plug it into x plus 1, we get -3. That's a negative number. So we don't even have to plug in to the absolute value because we know that the absolute value can't have an output that's negative. So this answer doesn't work. Now we'll check -2. When we plug that into the right side, we also get a negative number. So that also doesn't work for the same reason. We can't have the output of the absolute value equaling a negative number. So both of these answers resulted from correct math. We followed all the steps of the math correctly, but both of these are extraneous roots. The algebra leads us to think that they might be solutions, but it turns out that they actually don't work when we plug them into the original equation. So both our roots here are extraneous roots, and what that means is we have an equation at the top that has no solution. In summary, we solve the equation absolute value of A equals B by splitting it into two equations, A equals B or A equals -B. Remember, we have to isolate the absolute value before we can split it into the two OR equations. Once we solve for answers, we have to check that each works in the original equation. In this way, we eliminate extraneous roots. Another topic in advanced algebra is function notation. So first of all, I'll say the value of any algebraic expression of x depends on the value of x itself. So for example, here are 4 different expressions. We could plug in different values of x, and of course any input value of x would produce different outputs in each of these 4 expressions. Now, of course, with the expression 1 over x, we can't plug in 0 to that, but we could plug in any other number on the other line. For the other 3, we could plug in any number on the number line. We could plug in positive numbers, negative numbers, fractions, and of course, we'd get all kinds of different outputs if we plugged in different inputs. So, changing the value of x, of course, changes the value of the expression. Function notation is a way to formalize this process. A function is like a machine that takes an input and assigns it to an output. Different inputs give the same or different outputs. For the purpose of the test, a function is always associated with an algebraic expression. The input is the value of x we are going to plug in, and the output is the value of the expression once we plug in that value of x. So function notation, for a function with the name f, we write it this way. We write f and then we write the x in parentheses. This is read f of x. And this is not multiplication. We're not taking a number f and multiplying by the number x. F is technically what's called an operator. It is performing an operation on x. By this notation, we're saying that f is the input to the function f. Suppose f is a function that has x as its input and plugs this value of x into the expression x squared plus 4 and gives the value of that expression as its output. In function notation, we would write that as f of x equals x squared plus 4. In other words, this is the rule that says, give me any value of x, and I will take that value of x, I will square it and add 4. That rule is formalized in this function, f of x equals x squared plus 4. Suppose we take this function and plug a value, say x equals 3, into it. We would write f of 3 to denote that we're plugging 3 as the input into the function. To find the output, we'd simply plug x equals 3 into the expression. So f of 3 would equal, we'd plug in the 3, so it'd be 3 squared plus 4, 9 plus 4, which is 13. So the input of 3 has an output of 13. Here's some practice problems. Given this function, evaluate the following. You can pause the video and then we'll talk about these. Okay, so when we plug in x equals 0, then of course the first two terms is 0. We just get the negative 21, so that's going to be negative 21. F of 0 has an output of negative 21. F of 3, when we plug that in, we get 9 plus 12 minus 21. All that cancels and we wind up getting 0. So f of 3 equals 0. That is one of the roots of the function, one of the values that makes the function equal 0. When we plug in x equals negative 1, we get 1 minus 4 minus 21. When we add all this up, we get negative 24. And so this is the value of the function. Another practice problem. Given the function f of x equals x squared plus 4x minus 21, the same function we had last time, find the values of x that would satisfy the equation f of x equals 24. In other words, what inputs would give us an output of 24? Pause the video and work on this on your own. Okay, let's think about this. We're going to say that that expression equals 24. So really, we can ignore the f of x. What we really have is just a quadratic equation there. So of course, the way we solve a quadratic equation, we get everything on one side equal to 0. Then we factor it. This one can be factored into x minus 5, x plus 9. We get our two equations and we solve. So x equals 5 and x equals negative 9. These are the two solutions we get. And so what this means is that f of 5 and f of negative 9 both equal 24. Those are the two inputs that have an output of 24. The test will always give us the expression the function equals. The test will not expect us to find an unknown expression. But the test could give us an expression including an unknown value and ask us about it. So this is a very test-like practice problem here. Given the function f of x equals x squared plus kx plus 4, so there's a variable that appears, an unknown value, k, that appears in the function. And then the question is going to say, find the value of k if f of 2 equals 18. This is very typical of a function notation question on the test. So pause the video and then we'll talk about this. Okay. So when we plug 2 into that expression, we know that that expression equals 18. So we plug it in, we simplify a bit, we get the 2 squared plus 4, that's 8. Subtract 8 from both sides, so 2k equals 10. Divide by 2, we get k equals 5. So all we did really was plug in the value of 2 and set it equal to 18, and then solve for k. So far, we have seen many examples of functions with quadratic expressions. Not all functions are quadratic functions, but these are quite common on the test. Linear functions are quite easy, and the test can ask far fewer questions about them. Many other categories of functions are harder and quickly get into math well beyond the test. For example, trigonometric functions or something like that. These would never appear on the test. They're too advanced. The test may ask about slightly more difficult functions. So you may see questions about functions that look like this on the very hardest math questions on the test. So far, we have talked about plugging numbers into a function, but we can also plug algebraic expressions into functions. In the algebraic rule for a given function, x represents any input. So what we're plugging in for x doesn't have to be a number. It can be an expression. Rather than replacing x with a number, we could plug in an expression, and then we would replace every x in the equation with that expression. This can be conceptually difficult. Take a simple function such as f of x equals 3x minus 7. So this is a rule that says, give me any input, I'll multiply it by 3, and then I'll subtract 7. And that will be the output. Really, writing it that way, we could write it in this form. F of empty box equals 3 times empty box minus 7, with the understanding that we could put anything we want into that empty box as long as we put the same thing into the empty box on the other side. We could put a number into that empty box, we could put an expression into that empty box. And so really, what's going on, the x of the function equation is an all-purpose holder for anything, a number, an algebraic expression, or another function. So we have to expand our understanding of what it is, what x means, what it can hold as a variable. It can hold a number, but it can also hold an algebraic expression or even another function. For example, let's stick with this function, a nice simple linear function, f of x equals 3x minus 7. Then f of 4x, well, what would that mean? That means we're going to multiply 4x by 3 and subtract 7. So if we simplify this, we get 12x minus 7. F of 2x minus 5. We're going to plug 2x minus 5. We're going to replace the x in the function equation with 2x minus 5. And so we'll get this, then just multiply out, simplify, and we get 6x minus 22. We could even plug a quadratic expression into this function. So we're just going to multiply that quadratic expression by 3 and subtract 7. Multiplying everything out, and we get 3x squared minus 9x plus 15 plus 5. So here's a practice problem. Given this function, x squared minus 2x minus 1, find f of x squared plus 3. So pause the video, and then we'll discuss this. Okay, this is tricky. Every x in that original function expression, x squared minus 2x minus 1, every x is going to be replaced by x squared plus 3. So what we're going to get is x squared plus 3 squared minus 2 times x squared plus 3 minus 1. Now that first expression, that's the square of a binomial, the square of a sum. So we can use our square of a sum formula. Remember the square of the sum formula from earlier in our discussion of algebraic expressions. And so that's just going to be x squared squared plus 2 times x squared times 3 plus 3 squared. That's going to be how we square x squared plus 3. Then we simplify all that. We get x to the fourth plus 6x squared plus 9. That results from squaring the first term. Then we distribute the negative 2. We get negative 2x squared minus 6 and then a minus 1. Collect all the like terms, and we get x to the fourth plus 4x squared plus 2. And that is the resultant expression from plugging in the expression x squared plus 3 into this function. In summary, the notation f of x equals an expression means x is the input. We plug the value of x into the expression, and the resultant value of the expression is the output. So it's a formal way to pair inputs with outputs. That's what a function is. We can also plug expressions into the function as the input. In the formula of the function, we replace every x with the expression that we are plugging in. And you definitely will see problems like that on the more advanced math questions on the test. The next topic in advanced algebra is strange operators. What do we mean by strange operators? Well, think about it this way. Suppose you saw a question such as this. 3 and then some symbol 4. I don't even know what to call that symbol. Let's call it 3 star 4. 3 star 4 equals what? Obviously, we have no way to answer this because we have no idea what that strange symbol means. The test absolutely cannot give you a strange symbol and expect you to know what it means by that symbol. So that would be a totally unfair, illegitimate question. You will not see that on the test. But the test could define a new symbol by giving us this rule. For all numbers x and y, let x star y equal x squared times y. So in other words, what we're going to do, according to this rule, we're going to take the first number and square it and then multiply it by the second number. That's what the rule is. Okay, now that we have a rule, they could ask us to follow the rule. Then what is the value of 3 star 4? Now this is a totally legitimate question because they tell us what they mean by that symbol and then they ask us to follow that rule. So 3 star 4, we would just follow the rule given. We're going to square the first number and multiply by the second number. So that would be 3 squared times 4, which is 9 times 4, which is 36. So 3 star 4 has a value of 36 when we're following this particular rule. Sometimes the test will give you a problem like this. They'll give you a problem with a strange operator, some symbol that neither you nor anyone else taking the test has ever used as a math symbol before. So it's very important to realize every single person seeing the problem is going to see this for the first time. They are encountering this particular symbol used in this particular way for the very first time. The test will always give you the rule for following the symbol, and usually it's a relatively simple rule, and all you have to do is follow this rule by plugging some values in. You see, the test loves this sort of question because most test takers panic. Most people mistakenly think, oh no, my math teacher probably covered this and I forgot it. And they go into all kinds of modes of panic and shutdown. When you see this kind of question, don't panic. No one has ever seen this symbol before, and the rule for the symbol will always be there for you. So just because it's new, don't think it's new just to you. It's going to be new to absolutely everybody. Every single person seeing this question will be seeing this symbol for the first time. And so you're all starting on a level playing field. You just have to keep a level head and follow the rule that they give you. Here's a practice question. For positive numbers a and b, let a, and I'm not sure what to call this symbol, let's just say arrow. Let a arrow b equal a over a plus b. What does p arrow p equal? So pause the video here and then we'll talk about this. Okay, so this rule says that the first number is going to go into the numerator and the sum of the two numbers is going to go into the denominator. So p arrow p, that means we're going to get a p in the numerator and a p plus p in the denominator. Of course, p plus p is 2p. And we have p over 2p, the p's cancel, and we just get 1/2. So p arrow p has an output or a value of 1/2. Here's another practice question. This symbol here, it turns out, is a Greek letter, the Greek letter phi. For positive numbers p and q, let p phi q equal p plus 1 over q. So it's going to be the first number plus the reciprocal of the second number. What does quantity 1 phi 2 and then phi 3, that's a hard thing to say, what does that equal? So I'm going to say pause the video here and then we'll talk about how to evaluate this. Okay, so the first thing we're going to do is going to evaluate what's in parentheses. Order of operations tells us that parentheses take priority, so let's just focus on that one little piece in parentheses, 1 phi 2. So 1 phi 2, of course, that's going to be the first number plus the reciprocal of the second number, 1 plus 1/2, which is 3/2. I'll leave it as the improper fraction. Okay, Now we can replace that whole parentheses with its value. That parenthesis, everything inside the parenthesis has a value of 3/2. So we can just replace that. So 1 phi 2 becomes just 3/2, and we get 3/2 phi 3. So this would be the first number plus the reciprocal of the second number, 3/2 plus 1/3. We find a common denominator, and we get an output of 11/6, and that's the value. Here's another practice question. Pause the video, and then we'll talk about this. So, of course, the heart symbol, that's a symbol, we all know the heart symbol, but of course we never used it as a mathematical symbol before. So heart as a mathematical operation is new for everyone seeing this question. So we're going to say, let a heart b equal 2a squared plus b. So the first number gets squared and multiplied by 2, and then we just add the second number. What does 1 heart 2, heart 3 equal? Well, first thing we're going to do is set the parentheses. We're just going to treat that separately. 1 heart 2. 1 heart 2, what is that? Well, that's going to be 2 times 1 squared plus 2. 2 plus 2 is 4. So that whole parentheses just equals 4. So we can replace the parentheses with 4, and then it's 4 heart 3. Well, this would be 2 times 4 squared plus 3. 2 times 16 plus 3, or 32 plus 3, which is 35. So that whole expression has a value of 35. Notice that all the operations here, these are just basic arithmetic and algebra operations. Once you follow the rule, it's always very easy to follow. Once again, just remember not to panic. In summary, the test will give you strange operators that you and everyone else has not seen before. Don't panic, it's new for everyone. The test has to give the rule for the operator. It will always give you that rule. Simply follow that rule. Remember to find the numerical value of expressions inside parentheses first. You can replace the parentheses with the overall value of that expression.